Hi, this is the first of a series of videos about our carbon footprints. If we set targets of achieving carbon zero, we have to be able to give an estimate of our effects on carbon emissions. This is important because we all are dumping into the atmosphere. It is estimated that at current emissions, we have about 25 more years before we can no longer hold the temperature rise at the year 2100 to 2 degrees C. And if we are aiming at the safer level of 1.5 degrees Celsius, then we have to get our skates on now to achieve that in about the 7 years remaining. The carbon measure is called CO2 equivalence, or CO2e. That takes the measurements of emissions from all greenhouse gases, mainly carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and CFC, such as CF3H, which is fluoroform. The effects of all of them are normalized as if it was only CO2 emissions to estimate the total greenhouse warming in one figure. How these emissions arise can be plotted in many different ways. This version from Our World in Data looks at the sectors in our activities. A significant portion, as plotted here for 2016, were from the energy required for the production of iron and steel. So let's look at the example of iron and steel, which is about 1 o'clock in the wheel shown. The embodied energy and carbon of iron and steel represent what is needed to make 1 kilogram of these products from their raw materials. We aren't short of the element iron. It is the 5th most abundant element in the universe after hydrogen, helium, oxygen and carbon in descending order of abundance. In the Earth's crust, the known abundance is about 52,000 parts per million. That's about 2,000 times larger than copper, for example. But you can't dig it out of the ground as such because it is all oxidized by our atmosphere, much as Fe2O3, as in the mineral hematite, and some as magnetite, Fe3O4. The iron ore has to be reduced, that is, to have its oxygen removed, and generally the key reagent is carbon monoxide, which is oxidized to carbon dioxide, and there isn't much CO around, so all that has to be generated in the furnace by the reaction of coke and oxygen gas. Overall then, the reactions to form iron can be written as shown here. Energy is needed to convert the oxide into metallic iron, and this adds an extra 2 kilowatt hours of energy per kilogram of iron. This is more than recovered by the burning of CO to CO2, and overall there is an energy output of a little under 1 kilowatt hour per kilogram of iron. At the same time, there is a level of embodied carbon associated with the iron as CO2 is generated by the chemical process. But the processes involved in the mining, transportation and refining also require energy, much of which is not utilized, and so the energy generated by the chemical changes is dwarfed by all of that. The embodied energy is estimated at 7 kilowatt hours per kilogram, and the embodied carbon is approximately doubled to 2 kilograms of CO2e per kilo. Our simple equation simply doesn't cover everything. There are a few percent of carbon in the iron, and it's much to use left there from the blast furnace for most uses, and further treatment is needed. And the processes of more oxygen treatment release more CO2, and that requires more energy. Scrap steel can bypass the first step, and so less energy is needed to produce new steel from it, and the carbon footprint is lower. There's no CO reduction. Not surprisingly, it takes much effort to derive an estimate of the embodied energy in carbon. It will be a little different for every ore source and operating furnace, and there is some margin of error. But the value of using embodied carbon rather than energy is that it encapsulates both intrinsic emissions and also those required to drive the processes. Many differences are very clear. If we compare steel to aluminium, even though there is no intrinsic emission of CO2 in the manufacture of aluminium, its electrolytic reduction, The embodied carbon is much higher for aluminium, 10 kilograms per CO2e per kilogram of aluminium, as compared to virgin steel. Indeed, the important inventory of carbon and energy, ICE, only EC values are now listed, and for a good spread of common materials, there are sufficient studies to allow a statistical analysis to derive more reliable estimates of the embodied carbon of materials, for example in buildings. The ICE database tabulates these, as do books such as this one by Michael Ashby. Closer to ordinary day-to-day living is the recently updated book of Mike Berners-Lee, How Bad Are Bananas?, which has overall estimates of the things that we use, like houses and cars, and what we eat. The embodied carbon of something is a good starting point for measuring its impact on greenhouse gas emissions, and they are critical over the next few decades. The water footprint, normally called virtual water, VW, in litres per kilogram, is important too, and in some locations that can well be critical. Now, for example, if we consider the options for bottles and cans, we can note there is a big variation in terms of the virtual water. Aluminium requires 1200 litres per kilogram, PET 150 and glass 18. And there can be some critical decisions which are rather tricky about which materials to use, and we'll need to look at each of them in a little more detail to see how much material is needed to make an item useful, and the possibilities for uptake of reuse and recycling. And in the rest of the video series, we look at a collection of these choices to see what we use and what we might buy.